Hi everyone, this is the evolution of Julia. So on today's agenda, we're going to go over the introduction and history of Julia, basics like syntax, a deep dive, comparison, demo, and lastly, our conclusion. So the industry has a dilemma. We have scientists who write in Python to test math, and we have engineers who rewrite it in C++ for speed. This wall between math and hardware creates errors and waste. And as we can see, we have Python on the left and C++ on the right. Something as simple as printing hello world is much more verbose in C++. So the solution to this, to bridge that gap, is Julia. What is Julia? Julia is a high-performance dynamic language specifically designed for technical computing. To bridge this gap, it combines the ease of Python with the speed of C or C++. The core technology, it uses a just-in-time compilation to run code at native machine speed. And here's an example of what it looks like to print Hello World in Julia. Very similar to Python. Now we're going to go over the history. So this is the evolution of Julia. Its origins, it was created at MIT in 2009 by four students. We have Jeff, Stefan, Viral, and Alan. The philosophy behind why they created Julia was because they wanted Python's ease and C's speed, which is the best of all languages. It was publicly revealed in 2012 and it launched its first version in 2018. And as of today, it's now used by NASA and the Federal Reserve. Now we're going to go over the language analysis. So more about Julia, we're going to talk about the readability, writability, and reliability. Julia has a math-friendly syntax, so the code looks like textbook equations, and there's no curly braces, and it ends with the keyword end instead of using curly braces. For writability, it has a high-level abstraction, so there are no semicolons, no manual memory management, vectorized dot syntax, for example, A dot plus B. Next, we have reliability. It has type safety and garbage collection. For example, type interference catches errors and immutable structs prevents race conditions. Now we're going to go over some comparison with the syntax. So on the left, we have Java or C++, and on the right, we have Julia. So for Java and C++, arrays index start at 0, which is the computer science standard. But in Julia, the array index starts at 1, which is more mathematical standard. And this essentially aligns better with math notation. So on the left, we have C++, and on the right, we have an example of Julia. We can see that our array accessing the first element would be at 0. So we're accessing 10, for example. But on the right, to access the first element, we have to use 1 to access 10. So some key features about Julia, we have dynamic typing, one-based indexing, which we just talked about, and general syntax comparisons.
Hi, my name is Hiab, and I'm going to be going over the technical deep dive of Julia. So Julia uses JIT, or just-in-time compilation, which is primarily built on LLVM's on-request compilation technology, and that means that the code is compiled as the program is running. If we want to look at different languages to compare, C or C++ use ahead-of-time compilation, which means that the entire program is compiled before the code starts running, before the program's running, which means that it is fast, but it does lose flexibility. But if we want to look at Python, Python is an interpreted language, which means that the interpreter processes the program a little at a time, which does make it slower, but it does have flexibility. And Julia is kind of in the middle of that, where it can achieve almost C or C++ speed while also having some flexibility. So one of the trade-offs of Julia's just-in-time compilation is that the first call of a function is slow, And that is because Julia uses dynamic typing for its arguments in a function. And a function is called for the first time, Julia has to compile based on the types of each of the arguments. But after that, since it already compiled that one time, it doesn't need to compile that specific line again when the function is called again. Um, Another trade-off that Julia's JIT compilation has is that it trades off speed for memory. And that comes about when we have um, different calls of the function with different methods, different types of methods. It needs to compile for each change in the type of an argument, and it needs to compile every time, which takes up a lot of memory. But once we have some versions of the function with the different argument types, then it doesn't have to compile each time, so it can run fastly. Another feature of Julia is multiple dispatch, and it's one of Julia's core features, and that is when it chooses which methods to invoke based on the type of all the arguments and not just one of the arguments. Julia is not an object-oriented language, which means that its objects don't hold behavior, and multiple methods of and that means that we have multiple methods of a function instead of different classes with their own methods. And Julia is designed for math and science, and so multiple dispatch is one of its core features because in math, whenever there is an operation, each operand is that affects the operation equally, and therefore it needs to be considered. And it doesn't need to be just one argument that is considered.
So our project goal is to find a fair price of a financial option, which is essentially a contract to buy a stock later by simulating the stock market's movement by a million amount of times. I'm going to go ahead and run this program. And what we're going to notice is that it's extremely slow. And this is the thing about Julia is that the first time you run a program, it's going to be extremely slow. And that's just the consequence of why it's so fast later on. You just need to get it going. So unlike Python, which interprets code line by line, Julia uses a just-in-time compiler. But because of this, once the functions are compiled, it stays in Julia's memory, and the second time you run it, it runs as nearly as fast or the same speed as C. So it returns how many CPU threads it's using, how long it took to simulate a call and put option, and it returns our call price, put price, and our graph. So our call price, or when to buy the stock, is $10.45, and we should sell it at $5.50 based off of the parameters we gave it. So we said that the initial stock price is $100, our strike price is $100, 5% risk rate, 20% volatility of how the market is moving over a year span of time, and a million simulations or what if scenarios. We can run it one more time and we can compare how fast it is compared to the first time it ran. So a lot faster. And it's slightly different outputs. We have $10.44 for the call price and $5.58 for the put price. And one thing to notice is that the outputs are slightly different. And this is because um, every time we hit run, we're running a million simulations, which again are basically a million what if scenarios, and different outputs are due to how the random number generator interacts with multi-threading. So although we do have a set um, parameter, it will give us different call prices and put prices based off of the random number generator. And here's our graph that it generated. We have the running average price in blue and the final price in red. So now we're going to go over our second version. And this version, we decided to allow the users to input whatever they wanted. So we can say $100, risk-free rate, and So this one's a lot faster. Our call price with our inputs given, $39.30, and our put price is extremely low. And this is our graph for those inputs. The reason why it's so crazy in the beginning is because that's how many simulations it's going through. And if you do like 5 simulations, it's going to be like this because it's not getting enough simulations to determine what the price should be at. So we can run this one more time with different inputs. We can do inputs similar to the first program. So over a million simulations, and it should be very similar to what we got. Right. So our call price is $10.47, and our put price is $5.57. Essentially, what I wanted to do here is show how accurate it is compared to the first one. Very similar. So they're doing the same job. And this is our graph for this one. You can see again the running average in blue and the final price in red.
Next, I'm going to go over our application overview. So our goal was to make an app which tries to find the fair price of a financial option. And we did that by simulating the stock market's movement X amount of times. Some of the key features we used were threads, structs, and time macro to measure performance. And we used statistics, base threads, and plot packages. So some of the key features that we used in our application were we used multiple dispatch for our payoff function, and we used abstract types, and we used European option for that. We used threads macros so that we were able to achieve better time, better time efficiency, and we used time to kind of measure our performance. And we also used Unicode variable names. We used this symbol for volatility because it is the same symbol that is used in math, and we wanted to keep it consistent. And with Julia, we have that option because of the feature that is Unicode variable names. So the two main methods that we used were the Monte Carlo method and the geometric Brownian motion. So the Monte Carlo method is essentially a bunch of what-if scenarios that are repeated in random sampling with some level of uncertainty, and it is mapped out later to help us make decisions for our goal. And we use geometric Brownian motion as our model to predict future stock prices. And then we inputted that into the Monte Carlo method to simulate the results of the future stock prices. Some of the parameters we used were initial stock price, which was the stock price at the start of computation, and that was given in by the user. We used strike price, which is the target price that the user is looking for. We used the risk-free rate, which is the rate at which the stock grows annually. We used volatility, which is how much the stock swings. We used years of expiry, which is how long the user wants the simulation to go in years. We use number of simulations, which is how many different stock prices we are going to simulate. And for simulation steps, we used 1/252 because that is how many trading days there are approximately per 1 year. And we had that as a constant for our app. And that is how we did our app. What we learned from this experience, some of the challenges we faced were scheduling difficulties due to both of our times time conflicts. We had to communicate well to get over our scheduling difficulties. but that was overcome by just good communication and collaboration. Another challenge we faced was execution process issues because we were trying to execute our program in different processes, and it just took a lot of trial and error for us to figure out which one was best for our program. Another challenge was just the learning curve of getting familiar with new syntax, as we both hadn't worked with Julia before. But yeah, to conclude, some of the takeaways we have, we gained experience in a new language, which was interesting because we had, as I said before, we both hadn't worked on with Julia before, and so it was a good experience. We learned about new and useful features. Like, I didn't know about some of Julia's features, like multiple dispatch, and it's interesting. And it's just useful to know. And now I know that I can use Julia for some if I wanted a project in math and I wanted it to have the speed of C. We learned about execution processes, as I said before, that was one of our difficulties. It was a bit of a learning curve, but yeah, thank you.